All right, we're going to start taking a look at a polynomial. And now, in the last section, actually in section 1, all of these polynomials were factored for you. So finding the zeros or the x-intercepts or the solutions was nice because they was already factored. So what do we do if it's not factored for us to find the zeros? Well, that's where we're going to take a look at some strategies. We're going to take a look at some steps and theorems to help us. So first of all, remember a polynomial has many terms. And the fundamental theorem of algebra, don't worry, I'm not going to ever test you on it, but the fundamental theorem of algebra says that whatever the degree of the polynomial is guaranteed to have that many zeros. Okay? So we'll do this. Fundamental theorem of algebra states that a polynomial function of degree n will have n zeros or solutions. Okay? Now, those solutions might be real. Those solutions might be complex or not real, but it'll have that number. So if it's x to the 5th plus x to the 4th, etc., it's going to have 5 solutions, guaranteed. But those 5 solutions might be real numbers showing up on a real number line. They might be complex roots. All right, so what I want to do today, and we're going to practice, is we're first going to set up and determine some backgrounds on finding some roots, and then we'll practice. I'll probably do a separate video on actually solving once we've set all these up. Okay, so here we go. So there's a few things that we want to take a look at. One of them is what is called, let's kind of review here. Okay, let's think about what a factor is. A factor will divide into a problem evenly. A factor goes in with no remainder. Okay? So factors divide into a number or a polynomial with no remainder. So for example, think back to grammar school. Is 3 a factor of 15? Well, the answer is yes, because if I take 3 and I divide it into 15, it goes in 5 times and it has a remainder of 0. So it goes in evenly, therefore it's called a factor. Is 3 a factor of 17? Well, if I do the same argument, if I do the same setup, 3 is the divisor, 17 is the dividend, and if I do this operation, 3 goes into 17 5 times, and notice it has a remainder of 2. So somewhere around 4th or 5th grade, you learn to turn that into a remainder of 2 out of the 3 that we're dividing by. So we get 5 2/3. So this answer would be no, it is not a factor since it had a remainder. This one was yes, it is a factor since it has a remainder, which is 0. All right? So when we're looking at something now, same idea, it's just now it's a polynomial. we have something that's called the factor theorem and the remainder theorem. We're going to start with what's called the remainder theorem. Because everything, when you divide, everything has a remainder. That remainder might be a number, that remainder might be an expression, that remainder might be 0, but it has a remainder. Okay? So if we let f be a polynomial function, okay, let f be a polynomial function. So it's not going to have any fractions in it. There's going to be that the domain is all real numbers. It would be the ones that bounce, pass through, smooth, and continuous. Okay? If I take this function, if this polynomial, f of x, is divided by x minus some constant, then the remainder is simply f of c. So I could do long division, but I can also use the remainder theorem. So for example, let me give you an example. Find the remainder when here we'll do this one. When x cubed minus 4x squared minus 5 is divided by x plus 2. Now I'm going to remind you of long division. Then we can use the factor theorem. Okay? So I'm going to first do long division to figure it out. If we use long division, because we just practiced some of this in the last couple sections. If we do long division, this will always work. I could take x plus 2, that's my divisor on the outside. On the inside, because it's third degree, I would be expecting 3 answers. Because it's third degree, I need to have an x to the third term. Then I need to have an x to the second term. Notice there's no x to the first term, so I'm going to put in no x to the firsts. And then I'm going to put in my constant term. Okay, this didn't really show up very well, so let me try this. No x's, not an ox, but no x's. And now I'm going to start the division process. What do we multiply x by to get x to the third? Well, we multiply by x squared. Multiply that back, x to the third plus x squared times 2. Now we subtract. X to the third minus x to the third is gone. Negative 4x squared minus 2x squared gives us negative 6x squared. Bring down the next term. We may or may not need it, so we might need to bring down the term after that as well. And start over. What do we multiply x by to get negative 6x squared? Negative 6x. Negative 6x times x. Negative 6x times 2. Subtract. Anything minus itself is 0. 0 minus negative 12, and then I bring down the next term. And start over. We keep starting over until we cannot divide anymore. What do we multiply x by to get a first term of 12x? We multiply by positive 12. Distribute this back. 12 times x, 12x. 12 times 2 is a constant number, 24. Subtract. And most people make arithmetic mistakes on the subtraction. The x's cancel. Negative 5 minus 24 is negative 29. There's nothing left to bring down. What can I multiply x by to get a number? Nothing. So we're finished. So this would be our remainder. Here's our remainder. Our remainder is negative 29. Our remainder is negative 29 out of whatever we divided by. But our remainder was negative 29. Now that will always work. But that's pretty arduous, tedious. It takes a long time. So the other way to look at the problem is to use the remainder theorem. And it says, well, if f is a polynomial, which it is, it's got many terms, polynomial. If it is divided by x minus c, which it is, if x plus 2 is going into it, then the 0 out of that would be negative 2. So this just says the remainder is f of c. Okay? So if I use the remainder theorem, we are given our function. I'm just writing the problem down again. X to the third, 4x squared minus 5. If we choose to use the remainder theorem, don't look away because it's not going to take very long. All we have to do is substitute in f of negative 2. And the reason it's negative 2 is that would be the solution if I solve for x. If I move the 2 to the other side, it would be a negative 2. I could rewrite this as x minus negative 2. And that would be the x minus c. And now, welcome to Algebra 1. Negative 2 cubed minus 4 times negative 2 squared minus 5. Order of operations, do exponents first. Negative times a negative times a negative, negative 8, that's 2 times 2 times 2. Here I have to do exponents first before I multiply. Negative 2 squared is a positive 4. Negative 8, negative 16, negative 5. Negative 8 minus 16 is negative 24. Minus 5, look at that, you guys. We got the same answer. Same answer. One way is using long division, which always works. The other way is using the factor theorem, or the remainder theorem rather, which always works. So we found the remainder. The remainder is negative 29. That's all the remainder theorem says. It says substitute in the number, see what you get. Okay? Not bad. So, let's take a look also at what is called the factor theorem. because factors go into numbers evenly. So I left the remainder theorem up there on purpose because the factor theorem looks identical. And then there's one other step involved. All right? So the factor theorem says, okay, to start off the same way, we're going to let f of x be a polynomial function. So it's going to have many terms again. And we're going to start the same way. We're going to divide it. So it's going to start exactly the same. If f of x is divided by, I'm just writing the same thing down. Okay. Well, we already know what the remainder is. Then the remainder is f of c. We know that. We know that. Because that's what's going to happen when you do the division. But if it's a factor, okay, if it's a factor, two things happen. F of c, the remainder, is actually 0 because it goes in evenly, so there's no remainder left, which then means x minus c is a factor. So if it goes in evenly, if the remainder is 0, we call it a factor. We did that earlier with the numbers 3 and 15. 3 goes into 15 evenly with a remainder of 0. Therefore, 3 is a factor of 15. So on this last example, here we'll just do another example. Okay. Is, here, I'll choose one out of your book. Is x plus 3, I like to put it in parentheses, a factor of 2x to the, really? 2x to the 6th minus 18x to the 4th plus x squared minus 9. So this one happens to be, I just lost my place. This is number 16. So is it a factor? You have a choice. You could do long division, could take a while, but it'll always work. Or you could use the remainder theorem, which is also known as the factor theorem if the remainder is 0. I'm going to choose that. I'm going to choose to use the remainder or factor theorem. So if this is a factor, the answer would be x equals -3. So I am going to find f of -3, which would equal 2 times -3 to the 6th minus 18 times -3 to the 4th plus -3 squared minus 9. Now I don't know 3 to the 6th right away. Happen to have, oh, he's got some functions going on here. Let me do an all clear. Okay. Okay, hang let's do this. So this would be 2 times, well, let's see. A negative to the 6th power is positive. My husband's got that all set up for his calculus class, so I'm just going to do 3 to the 6th. So this would be a positive 729 minus 18 times, well, a negative to the 4th is a positive, 3 to the 4th is 81, plus negative squared is a positive. So this gives me 1,458 minus 1,458, and then those two canceled. So look what I end up with. So I end up with f of negative 3 equals 0. So is this a factor? Well, factors happen whenever the remainder is 0. Notice what we ended up with. When we substituted in what we thought was a 0, we got 0 for a remainder. So what does this mean? This means that, because this is the point, we know this, when x was negative 3, the y value, the remainder, is 0. Since the remainder is 0, that means x plus 3 is a factor since it went in evenly, and we have a remainder of 0. So the remainder theorem, you substitute in your value. Whatever your answer is your remainder. If your remainder happens to be 0, it's called a factor. Notice it's also called an x-intercept. If the remainder is not 0, it is not an x-intercept. It's just a point on the graph. So in this case, f of negative 2 is negative 29. That's just a random point on the graph, not a 0, not an x-intercept, just a point somewhere. Okay? So that's how we use the remainder or the factor theorem. We substitute it in and come up with whatever the answer is. You will always get a remainder. If the remainder is 0, we call it a factor. If the remainder is not 0, it's just not 0. Is it always like that? Yes. Yes. Okay. All right. And remember, earlier, notice the degree. The degree of this polynomial is the highest exponent. Well, the highest exponent we see is a 6. So that means we have at most 6 solutions. And we could have 6 real number solutions. We could have less than 6, but we're guaranteed to have 6 answers. Some might be real, some might be complex. All right, and we'll look at those complex answers in the next section. Today we're looking at real. Okay, so we looked at the remainder theorem, we looked at the factor theorem. The next one we're going to look at is what's called the rational root theorem. You might remember this as like P over Q's. Some of you have no idea what I'm talking about. Others might be like, oh, I kind of remember that. The rational root theorem is very helpful in that it gives us potential answers. First of all, real numbers are either called rational or irrational. So rational numbers are anything that you can write as a fraction. Rational numbers are whole numbers. They are integers, which are the positives and negative whole numbers. Okay. They can be natural numbers, which are the counting numbers, 1, 2, 3, 4. Anything at all that you can write as a fraction. So they can be decimals if they're terminating, if they end or repeat. And of course they can be fractions. Anything you can write as a fraction. So we have what's called, and this is an awesome theorem, it's called the rational root theorem. Or rational roots. I don't remember if it's singular or plural. I think your book might call it the rational zeros theorem. Let me double check. They do. They call it the rational zeros theorem. Same thing, right? Because we know zeros are x-intercepts, which are solutions, which are roots. So those are synonyms. Okay. So the rational zero theorem says, let f of x be a polynomial function. And I'm going to sort of rewrite it different than what the author in your book has. I'm going to write it this way. I'm going to call this a q, x to the n, plus, and I'm going to go all the way down to x to the first plus our last value of p. Because what's nice is a list of possible, doesn't mean they're guaranteed, rational, now remember that's a real number, so no imaginary numbers for this one. A list of possible rational roots can always be found by taking the factors of the very last constant number at the end divided by the factors of the very, very first coefficient at the front end. Okay. So, let's take a look at an example and let's just kind of see what we can come up with. Let's pretend that, let's let f of x equal 2x to the 5th minus 3x to the 4th plus x squared minus 7x plus 6. Okay. First question. How many zeros, how many roots, how many, here we'll call them zeros, which are also called roots, which are also called solutions, will f of x have? Well, we are guaranteed, whatever the degree is, that's how many solutions there are. We are guaranteed that because this is x to the 5th, we are guaranteed 5 roots. Now they might be real, they might be imaginary or complex, but we're guaranteed 5 of them. And in the next video that I do on finding them, I'll show you a way to help figure out how many you might have. Okay? Now that we know that we have at max, at most, we're going to have 5 of them. Let's list possible rational roots. And this is one of the fastest assignments you're going to have, because notice the second word, possible. Notice the first word, list. It doesn't say find them, it says list possible solutions. List possible solutions. Oh, and since it says rational numbers are real numbers. So we're not talking about anything that's imaginary. We're not talking about anything that's complex. So these are going to give me real solutions. Which means if it's real, it shows up on the graph. Which means these are all x-intercepts. All right, here it is. I'm going to follow the directions. It says we want to take all the factors of the last value p. Okay? So here is the p value. And we want to divide it by all the factors of the leading coefficient. Here's q. So possible rational roots would be factors of p over factors of q. So that's going to be factors of 6 over factors of 2. Do not reduce. Do not reduce and make that a 3 over 1. We have to list them all. So let's think about all the numbers that go into the number 6. Starting with 1. Well, we would have 1 times 6, 2 times 3. Or we could have negative 1 times negative 6, negative 2 times negative 3. So all the factors of 6, positive and negative 1, positive and negative 2, positive and negative 3, positive and negative 4. All the factors of 2, well, 2 is prime. So the only numbers that go into 2 are 1 and the number itself, 2. So positive and negative 1, positive and negative 2. And oftentimes people refer to this as the P over the Q. And you're finished. You're finished. It says list them. So we did. And it's fine to leave it this way. Do not reduce anything. You just list the factors. The next video, I'll show you what we're going to do with those, but for now, we're just listing them. Okay? So we can do it again. Given f of x equals negative 3x to the 4th plus 5x cubed minus 2x squared plus x plus 10. At most, how many answers are we going to have? Well, we're guaranteed 4 answers. Okay? So how many real zeros, solutions, can f of x have? Well, if those are zeros, those are x-intercepts. So we want to know, is it going to bounce, pass through, how many of them are going to have? Well, whatever the degree is the guaranteed number of solutions. So we could have 4 real answers. We could have 4 complex answers. But we can have 4. Since the degree is 4, that's how many we can have. We cannot have more answers than the degree. List possible real, remember that's a rational number, zeros. So we're just listing them. That's the P over Q thing. We're just listing them. They don't have to be the answer. These are just possible answers. Possible answers. So let's do this P over Q. Well, our p-value is your very last constant term, and the q-value is your very first leading coefficient. And it does not matter that one of them is negative, not at all, because as we noticed up above, positive and negative numbers go into all of these. So do not worry about that negative. That negative would tell you when you're graphing, the ends are going to behave like it's going down because it's negative. So I want all the factors of 10 divided by all the factors of 3. We don't need the negative because we always end up putting both positive and negative down. So the factors of 10, any number that can go into 10, positive and negative 1, 2, 5, and 10. Divide that with all the factors of 3. They're not always going to be prime numbers, but we end up with a 1 and a 3. Okay, so the first part of this lesson is just setting up how to determine what possible answers are. And then I'm going to do a second video here right now on how to solve once you've set it up. All right? So until next time, which will be a few minutes from now, bye.